Hello, today we're going to look at some more properties and one more proof. We're going to look at properties of scalar multiplication with matrices, and then we're going to prove one of those properties together. So we're going to look at four properties. So let's begin by setting the stage and letting us know what our variables are going to be for this theorem, and then we'll state those four properties. So to begin with, we're going to define two matrices and two scalars. So we're going to let A and B be M by N matrices, and KP, K and P really, be elements of R. So we have matrices A and B, they're the same size, and we have two scalars to work with. We have K and P. So our first property is going to be kind of like a distributive property. And we're going to say if I have K times A plus B, then that's going to be the same as KA plus KB. Right, so I can distribute a scalar over matrix addition. That's what this is saying. Now, we have a second property that's also like the distributive property. And that says if I have in parentheses K plus P times a matrix of A. So this time, instead of adding two matrices, I'm adding two scalars and then multiplying it by a matrix. That's the same as KA plus PA. So not only can we distribute scalar multiplication over matrix addition, we can also distribute scalar multiplication over scalar addition, really. Third, we're going to have an associative law for scalar multiplication. And that just says if I have K times, and then in parentheses, PA, that's going to be the same as KP times A. In other words, if I have the matrix 2A and I multiply that by 5, that's the same as multiplying A by 10. Right? I'm going to do 5 times 2 to get the 10. Now we're good to go. And last property that we're going to look at is multiplication by 1. So if I take the scalar value of 1 and I multiply it by a matrix, nothing happens. Right? And this makes sense because our scalar multiplication says take 1, multiply it by each entry in A. But 1 times any real number is itself. So we're just going to get A back again. So I think for our proof for this set of properties, let's prove 2. So let's prove this distributive property. And that'll give you some idea to think about, okay, how might I prove this distribution property? So I'm going to erase the board and get ready to do that. So let's get started. All right, so now I have some clean space to write our proof. So that's what we're going to do. Now, just a reminder, when we do a proof, we want to start with one side of this equation. We're going to write it over here, and we're going to have equals, and then we're going to start basically like simplifying that equation until we get to the other side. Now, in the previous video, we saw that that meant we had to take our matrix notation, split it up so that we were in terms of real numbers. In other words, in terms of the matrix elements, like the objects in the matrix, then apply properties of real numbers and kind of expand back out again. So we're going to follow a similar process here. So to begin with, again, we get to pick one side to start out with. You know, it doesn't really matter for this one either. So heck, let's start with the right-hand side this time. Let's see where this takes us. So I'm going to start out with KA plus PA. And my first move is to get this in terms of the matrix elements. So I'm going to write A as Aij in both instances. And this is just matrix notation. That's what allows us to do this. Now you have to resist the urge to like factor this out and immediately get to your conclusion, because we don't know that we can factor out matrices yet. That's what we're trying to prove. So we're not allowed to do what we don't know, right? So what we do know is we know how to find the scalar product. So I know that if I have K times a matrix, well, I just multiply each of those entries by K. So this piece here is going to become the matrix whose elements are K times the ijth element of A. And same thing with P. So this is going to become the matrix whose elements are P Aij. And this is our definition of scalar multiplication. Now, the reason this is nice is because it has taken these scalars that were outside the matrix and brought them inside. So now we just have matrix plus matrix, which means we can add them, and we know how to add. So this is going to be the matrix K Aij plus P Aij. And this is our definition of matrix addition. That's what allows us to do this. Now, this is super nice because we took this thing of separate pieces, brought them all together into one matrix together. So they're all able to play together now. And K is a real number, P is a real number, and the Aij is also a real number. So we can apply properties of real numbers. In other words, now we can factor because Aij is a real number, so we can factor that out of this expression. What that's going to do is over here, the K and the P were separate, and here they're together. So when I factor that Aij out, that K and that P are going to be brought together. So we get K plus P, and I'm going to choose to factor the Aij out on the right-hand side, just because that's how this is expressed here. So this is because of the distributive property of real numbers. Now we have this thing times the Aij, which is really just like something times Aij inside the matrix. But for instance, we know if we have something times Aij, well, that's a scalar multiple. So we can kind of go backwards with that definition. In other words, I can rewrite this as this scalar value times the matrix whose entries are Aij. And this is just using our definition of scalar multiplication in the reverse order. And now I'm super happy because we have just Aij, and that's our matrix A. So this is K plus P times our matrix A. Because of our notation, QED, we're all done. Yay. So just to summarize this process that we're going through here in this proof is we're starting out with one of the two sides. If you look at this proof from bottom to top, it'll get you there exactly the same. So in this case, we started with the right-hand side. That doesn't really matter in this problem. So we started here, and then we did, okay, let me put it in terms of real numbers, because we know what we can do with real numbers. We don't quite understand matrices fully yet. Then we can bring everything together so that we are allowed to play with them. They can all interact once they're all inside the matrix together. And because these are all real numbers, now we can apply properties of real numbers to help us get where we're trying to go. So again, you're starting out with something kind of separate. You want to bring it all together so everything can play with each other. And then you want to kind of bring it back out again so that we have our K plus P outside the matrix. We have just the Aij left alone up there. So like I said, use this proof as some guidance to think about the proof for our first distributive property that we stated for scalar multiplication. In our next video, we're going to look at properties of matrix multiplication. We've already noticed that matrix multiplication is not commutative. So does it have any of the other properties we're accustomed to? And if so, which ones does it have? So I look forward to seeing you in that video. And yeah, until then, have a great day.